Hello, my name's Ty Newell, and this is a talk on managing moisture and human-centric metrics in high performance homes. And the goal is to keep us healthy, comfortable, and productive. I'm coming to you from Urbana, Illinois, and these days, as most of us lament, I wish I could be there with you, but unfortunately cannot. But I hope you'll invite me back in the future. In any case, thank you very much for inviting me and giving me this opportunity to speak to you at PHMass. So the two talks pushed together, but with a common goal of creating healthy indoor environments. I've split the talk into one discussion on managing humidity. And of course, it's a very large topic in and of itself. And then the second on human-centric metrics, basically how to create a healthy indoor environment, what we need in terms of ventilation, air filtration, and the management of an indoor environment that keeps us healthy and productive. A couple of years ago, I had the opportunity to pass through Amherst, and Massachusetts is ground zero for progressive building. New Englanders, you've been there, done that. You know how to seal homes, you know how to insulate them better than anyone. And now it's time to focus and concentrate on making that indoor environment healthy. There's a lot of problems. A lot of you that have been associated with these projects are seeing those, and moisture is one of those. It's an area like this bagel shop in Amherst that was dripping wet on its ductwork and dripping wet on the inside of its windows on this particular day. A pretty nice day outside, but inside the moisture wasn't handled properly. And of course, that impacts our health. Each of these data points is from a military base in the US and represents dozens of homes. Our contract military housing is horrendous throughout the country. And for every house, and there's a lot of them with visible mold, 25% of those homes have an occupant with environmental health problem. We need to correct this problem for our readiness of our military and for their health and well-being. And the rest of us, this isn't too different than what we see in many homes around the US. So indoor moisture, what do we generate inside from the plants that we like to grow? We have about 60 plants in Equinox house, my house that I'm broadcasting this from. Kitchens and cooking, laundry rooms, bathrooms, and basically about any other activity of a human. When we look at how much we generate within a house, it's somewhere between 1 and 5 kilograms or liters of water, about 2 to 10 pints of water per day that we release as vapor as washcloths dry out, as the floor and walls in the shower stall dry out. And our respiration, our breathing is a major contributor. If you cook with gas, each gas burner is like having 5 people breathing heavy in your house. And so we have various sources of moisture. We're going to study what happens in moisture in an example home, a 2,000 square foot, 3-bedroom with 2 occupant home. And we're going to follow the story of 3 contractors. Contractor Luce, who builds a conventional home with about 6 ACH at 50 pascals on a blower door test. And contractor Type, who is sealing to passive house levels and then using either ASHRAE or passive house ventilation. And even though they have different formulas, ASHRAE 62.2, which FIAS now is aligned with, and Passive House Institute, which uses a 0.3 ACH or a minimum of 18 CFM per person in a house. These actually parallel each other quite closely, even though the formulas look different. And contractor Type could be a passive house builder who seals to 0.6 ACH while using ASHRAE ventilation. And then a smarter way to ventilate, sensing carbon dioxide, sensing the volatile organic compound level, and then bringing in fresh air when those get high because of occupancy and occupant activities. And then when those drop down low, not needing to ventilate. And the difference is very, very significant. We can see that contractor loose adding up the infiltration through the house on a typical wind type day with ASHRAE 62.2 ventilation, 90 cubic feet per minute for this house, that there's 230 CFM of airflow. Contractor tight has significantly reduced the infiltration load, which is a good thing because you don't always know where that air is coming from. And that adds up to somewhat less than half the amount of airflow of contractor loose. Good energy benefits as well as moisture benefits. And then when you build tight but ventilate smart, you can further reduce the amount. In this case, where this couple is in the house for 16 hours a day and 8 hours a day, no ventilation is needed, that overall about 27 cubic feet per minute on average would be brought into this house, a significant reduction from the other two. And if you think that that's a drastic reduction, too drastic, think about our respiration. If I delivered fresh air directly to your nostrils, like in a spacesuit or a scuba diving suit, that this would be about 0.27 cubic feet per minute. So we're still supplying more than 100 times what you need for breathing. But in smart ventilation, we're distributing it to where you are. We're also doing filtration through recirculation that one and done type ventilation, constant flow ventilation through a house doesn't do. And so we're actually doing a much better job than constant flow ventilation as specified by ASHRAE standards with much less airflow. And that's because we're not wasting it in unoccupied areas. We're not wasting it when no one's at home. So contractor loose. We take a look at a house and using an Urbana summer, but not so different from Massachusetts, where in the midst of our summer on average, it's 77 degrees and 70% outside humidity, pretty muggy conditions like what you get to experience. And inside, we'd like to keep it about 60% humidity and 72 degrees. Not a lot of cooling needed in a well-insulated home. And even if that air goes through an HRV or an ERV, the moisture management is not supplied through an HRV. And surprisingly, even though most people think it is, not handled properly through an ERV. And if you'd like the field data, understand the lack of moisture handling ability of an ERV, something that presumably with its mass exchanger helps you balance the moisture. Read Joe Stabrook and Building Science Corporation's report to NREL on several homes that were monitored over a couple-year period in Houston, comparing ERV moisture management to dehumidification moisture management. And you'll see that the ERV came in last. Why? Well, if you're exhausting from 100% moist bathroom to a 70% outdoor environment, you're actually going to be adding indoor moisture back into that outdoor fresh air stream. So you want to think twice about an ERV being better than an HRV in moisture management and energy recovery. In contractor loose's case, there's about 78 pints per day of moisture to handle when you add up the occupant activity moisture generation and the moisture supplied through infiltration and ventilation. Contractor tight, somebody building and then ventilating on either ASHRAE standards or FIAS 0.3 ACH standards, cuts the moisture load more than half, a substantial benefit, both in terms of energy loading and moisture loading, to about 38 pints per day. But then we ventilate smart, bring in air when we need it and deliver it where we need it within a home, and making use of sensors to know when the air is not fresh enough, And so in this case, as we mentioned, for contractor smart, about 27 cubic feet per minute on average. But the actuality is that when people are home, we're delivering a significant amount of airflow, in this case, about 20 CFM per person, equivalent to the intended exposure of ash rate 62.2. And we see that we've reduced the moisture load again, dropped it by more than half from contractor type. Now, in order to handle that moisture, just a couple of brief notes on today's methods and in the foreseeable future. There's no magic bullet coming along. Yes, there's other phenomena, but there's nothing special that's going to significantly change this picture. That in terms of an energy factor, the energy it takes to remove an amount of water from the air inside a home. These lines show us what a mini split heat pump, which is actually a pretty efficient dehumidifier. The problem with heat pumps in general is that they have a limited amount of dehumidification capacity relative to the cooling that they deliver alongside of it. And in striving for higher and higher SEER values, higher efficiency values in air conditioners, the manufacturers are actually lowering their dehumidification capability. They're going in the opposite direction of what we need in today's highly sealed, highly insulated homes, which, while it's a reduced amount of moisture management, it's a much more variable amount of moisture management that needs larger relative dehumidification conditioning capacities compared to the cooling, the sensible cooling capacities. And so we have to do something else, and that's adding in these open circles a dehumidifier, a machine that's made specifically to get moisture out of a home. But unfortunately, a dehumidifier does it at the expense of delivering the exhaust heat into the home. And when we're in the summer condition, using a dehumidifier means that we have to air condition that exhaust heat back out of the home. And what this plot basically shows is that we're somewhere around 1.5 to 2 kilograms or liters of water removal per kilowatt hour of electrical energy. So it costs about 12 cents in order to remove a liter of water. And that's actually a good deal. And we see that the open circles, the dehumidifier rating levels that are marked on the package, when you account for having to remove that with an air conditioner, the solid circles show the adjusted actual dehumidifier performance. And it's actually quite similar to what today's heat pump air conditioner would remove in efficiency. But the difference is that you can keep removing moisture with a dehumidifier, where an air conditioner can only remove a certain fraction of its air conditioning capacity. And when you're in swing seasons, an air conditioner is going to overcool. And when you're in the summer, a dehumidifier is going to overheat the house. So you need both in order to move to that humidity and temperature level you would like to have for your preferred comfort. You need both, and you need smart controls to be able to manage that. Let's look at some real data. The house I'm sitting in, as I mentioned, is Equinox House. It is a high performance home. It's sealed to 0.5 ACH when it was built 10 years ago. It has a heat pump in its smart ventilation system that also contributes to the dehumidification of the house as it's recovering energy. And then it has a heat pump water heater, which adds an additional beneficial contribution to moisture management. Well, when we look at how much moisture needs to be removed each day, doing this for over 50 years, it takes a lot of activity. It's pretty boring work, but basically filling up a bucket from the condensate hose, from the air conditioner, from our smart ventilator, from a heat pump water heater. And what you find when you do that is that some days you need very little dehumidification, other days you need a lot. And when we look at it in a cumulative basis over the course of a summer, we need to remove about 700, 800 liters per summer. And we find that today's modern mini split heat pumps and heat pumps of other flavors, the characteristics are similar, that more than 50% of the moisture handling does come from the air conditioner. The smart ventilator removes almost a third of the moisture, and the heat pump water heater contributes an important amount. If we want to see whether or not we can predict this using our zeros model, which is free to use online software, in addition to energy and moisture analysis, and this is software that's verified with DOE's best test software validation for building modeling. So this software is very accurate using average weather conditions to do the latent loading. And I meant to mention that it does economic analysis, it does financial analysis, and it sizes your solar array. But it's design software, not certification software. So it's a design aid to help you figure out the complexities of moisture management as well as energy balancing in a home. So we see that actually we can do a very, very good job with this software tool. This was a droughty year, so you get kind of a perspective of what a drier year than average would be. And of course, a wetter year might be somewhat more than that. Well, does this moisture management, is moisture manageable? Our lab is a 4,500 square foot Morton building, not something you might picture as a net zero building, but it's well insulated and it's 3 ACH at 50, so reasonably well sealed for a building of this type. And during this period in August, it was totally conditioned with a 1-ton ducted mini split heat pump with a temperature set point of 73. The building's net zero with an 8.5 kilowatt solar PV array. Here in the first part of August, just this past August, you can see the building floating in temperature when outdoor temperatures were somewhat cooler. The smart ventilation system would see that it was cooler outside and like automatically opening a window, except the smart ventilation unit would bring in fresh air and fill our lab building with fresh air, and it would be filtered air too. Once it got warmer for a period of about a week, you can see that the air conditioning was needed to keep us pinned at 73. We started going back into a swing season like temperature that was cooler. We could again take advantage of these nice cool nighttime temperatures to bring the building down. We had free conditioning. On the moisture side, what's this period of time represents is that nice muggy weather like what Amherst was experiencing a couple of years ago when I passed through. And with our controller set at 55% humidity, this screenshot shows that the inside of the building was 73 with 53% humidity. With a 55% humidity set point, that means plus or minus 2% humidity control. And the outside was a remarkable 71 degrees and 99% humidity. And of course, the air inside with smart ventilation is exceptional. So here we see that despite the very high humidity level outside, that this system, which consists of a 1-ton ducted mini split, and then also 70 pint per day inline dehumidification, and the modulation and the control of both the mini split heat pump and the inline dehumidifier were managed by the smart ventilation system. And there's some synergies that also occur, and we won't go into the details of that, but read our August newsletter from just a couple months ago to read about this in more detail, as well as a house in Chicago that implemented this control strategy. But you can see that through August, this building's humidity was kept at a very comfortable level within plus or minus 2% of the 55% humidity set point. We turned off the dehumidifier and just let the air conditioner control the building. And as you saw, the temperature never went out of control, but here the humidity quickly climbs to 65 to 70%, a very clammy indoor environment at these temperatures. We switch it back on, it quickly comes back into control. This dehumidification strategy works. We know how to manage humidity in all conditions, from Florida to New England and everywhere in between. So on the energy side, when we look at the electrical energy that these all electric, this example home for contractor Loose, Tight, and Smart, we see that yes, contractor Tight with ASHRAE ventilation drops 2,000 kilowatt hours. But when we ventilate Smart, we can drop another 1,000 kilowatt hours in overall electric load. And 1,000 kilowatt hours, that's 3,000 to 4,000 miles of electric vehicle driving. It's energy that we need that we can put to use elsewhere to live sustainably. And it's going to take you a few pots of coffee, but if you'd like to have more depth in all of these subjects related to moisture, go to our website. These are free reports that you can download. Now talking about human-centric metrics. And we've been working with Passive House folks of both flavors for many years. This is from 2007 when Dr. Weiss and Katrine Klingenberg visited my laboratories at the University of Illinois prior to my retirement. But as I tell people, while I'm retired, I'm not tired. And here are two of the early certified passive houses built in the US, built right here in Urbana, Illinois. And Joe Stabrook, on a very recent ASHRAE podcast that you can listen to, had a great idea. He said, you know, instead of this debate that we've been having at ASHRAE on the 62.2 committee of, do we have too much ventilation or not enough? So why don't we get smart about ventilation? Why don't, you know, we've got sensors that can measure CO2 and VOCs. Why don't we do that? You know, if I can have an iPhone that can give me 14,000 songs of music, I should be able to smartly control my building. And it's a great idea. And if you know Joe, let him know, yeah, it's a great idea. But also let him know it already exists. The house that I'm sitting in, I can ask Alexa what my CO2, what my VOC levels are, and I can tell Alexa to ventilate at a certain level and change my temperature. And then I can ask Alexa to play John Coltrane's Giant Steps. So the future is here. It's now, and it's been here. So we're going to talk about you. We're going to talk about a concept we call pre-ventilation and human-centric metrics, putting you at the forefront of building design, that you're not a constraint, you're the objective. Energy is a constraint, not the objective of building design. We live in a sea of energy, and we're not going to run out. The sun's energy is plentiful, and there's more than enough for all of us to keep us comfortable and healthy and happy. And so what makes you is very complex. There's ventilation for sure. There's what you eat, how much you exercise, the people you interact with, how much time you're inside, how much time you're outside. All of these things impact you, as it impacts Barrett, who just turned 5. And I'll tell you, you put a Slurpee in that guy, you got a different kid. So what I would like to suggest that you think about is separating the human needs from the building design. Because right now, when we design a home or a commercial building, it's building centric. ASHRAE's building standards and Passive House building standards, which parallel each other. A 2,000 square foot, 2 to 3 bedroom home. FIAS's alignment with ASHRAE, which is a good thing, gives you about 80 to 90 cubic feet per minute of ventilation specification. And Passive House Institute's 0.3 air changes per hour leads to a similar 80 to 90 CFM. So they tend to parallel each other. And the problem is that when you design in this manner, following whatever certification, that ventilation is simply a checkbox, and it's much, much more complex than that. So I think we need to concentrate on building design to make it energy efficient, avoid thermal bridges, make it durable, protect it from moisture. And while it's very directly linked to the human, do a better job looking at the human needs within it. And what we need is 800 parts per million of carbon dioxide, which essentially means doubling today's unacceptable ventilation standards. And the benefits we get by doing human-centric design and looking at the environment we're putting ourselves in is that we're going to increase productivity. We're going to have fewer sick days. Fewer of us will be dissatisfied with air quality. And the dollars associated with that much, much outweigh any potential dollar increase. But in general, when you ventilate smart, you'll also see the energy dollars drop too. Human-centric indoor air quality and comfort management essentially means that this cloud of systems in the background, not obtrusive, but it follows you. Whenever you enter a doorway into a building, into a home, these things kick on to keep you comfortable and to keep you healthy. Fresh air is brought in and it's filtered at a rate that keeps the carbon dioxide at 800 parts per million or less, something that your brain functions much better in, something that dilutes contagion so you get sick less often. Similarly, rather than just relying on this fresh air input, it is essential that we recirculate and recirculate through a filter. Recirculation in our homes does two important things. It takes unused fresh air that's stored in the unoccupied areas of our home and it delivers it to the occupied areas. And it's your opportunity to get particulates out of the home. It is not true that a passive house is a dustless house. It is absolutely a dusty environment without recirculation and filtration. And for your health, and as another means of reducing contagion concentration, bringing this through a filter and potentially taking it through something like ultraviolet germicidal irradiation to further kill any microbes passing through is a good thing to do. And then having something that can manage the temperature to the level that you like and something to manage the humidity. And we find from our field data that even though it may only take candle power to heat your home in a highly insulated and sealed home in a harsh winter environment, we still need 1 ton of heating and cooling for human needs. When you would like to sit down and read a book and your metabolism is low and you maybe like it a bit warmer, that you need about 1 ton of cooling or heating capacity to move to that desired temperature level in a reasonable time. When you've been exercising and you're actively working in your house, you need a similar amount to bring the temperature down. This is from real field data. You can find these reports on our website. And I'll just mention, if 1 ton's good, consider 2 tons. 2 independent 1-ton mini splits, for example, which operate 20 to 30% more efficient than a single 1-ton unit. It's the opposite of what you're used to thinking about. Adding 2 1-ton units operating at 50% capacity compared to a single 1-ton unit at full capacity, that these are 20 to 30% more energy efficient, plus you get resilience, plus you get zoning capability, and you get that at just a few bucks per square foot. And when we're seeing homes go up at $500 a square foot in regions around the country, can't you spend another couple bucks a square foot on your comfort? Leaky homes, it's a myth that they have good air quality. Here's a 1950s era home, about an 8 ACH blower door level home. When 2 young children who share a bedroom go to bed, it quickly rises at very high levels of carbon dioxide, indicating that if one child's sick, the contagion concentration is high and the other one's going to get sick. And indeed, that's what happens. The parents open the door at about 9 o'clock when the children quiet down. You can see it levels off, but it's at unacceptably high levels that does impair sleeping through the night. And it's very complex. This is much more complex than temperature and humidity control. Pollutant control is very, very difficult, and it's hard to do well. Now, the best way to describe today's ventilation standards, whether FIAS or FEE, is that it's too little, too much, but it's never enough, at least not where you are and within the home. If we look at a small house using ASHRAE ventilation standards, we have about 52.5 CFM, 13 cubic feet per minute per person. This house would always be polluted whenever it's occupied. And when we look at a large home, even though it looks like there's plenty of airflow per person, a 4,000 square foot home with 2 people would have nominally 80 CFM per person. But you divide this airflow among 10 different regions in the house, the 4 bedrooms, a den, a family room, a kitchen, a dining room, a living room. You're getting maybe about 15, 16 CFM per room. You put 2 people in it, you only have 8 CFM per person. Again, it's underventilated in the occupied areas. And then today's building standards, it makes no difference between sleeping and exercising people. It makes no difference between electric and gas cooking. And as I mentioned, a gas burner is like having 5 people, each gas burner like adding 5 people inside your house, except you get a lot of other bad pollutants along with it. So we need to ventilate smarter. And just to show between a one and done type ventilation system, no recirculation, just delivering ASHRAE ventilation standards in this certified passive home, this couple, when they're home, CO2 and VOCs are uncontrolled. When they leave for about a week, CO2 and VOCs it's overventilated, wasting energy. They come back home and it starts getting polluted again. With smart ventilation, anytime, no matter how many people might be there, no matter what you might be cooking, that CO2 and VOC sensors initiate these ventilation periods to keep the air quality at a good level. I just want to briefly state that comfort is not just a nice thing. There's money associated with it. This idealized plot of data from Fisk and colleagues on how our productivity is related to our comfort. For every degree that you're outside your comfort range, you drop about 1% in productivity. If you're earning $50,000 a year, that's $500 drop in productivity, and the associated cost of giving you the temperature level that makes you feel most comfortable is much, much less than that $500 value from making you more productive. Just to give you an indication of how quickly we pollute a room, here I am sitting in our test chamber at our lab. It's about a 6 to 7 foot cube. Seal me in, put about 1.5 cubic feet per minute of infiltration through that chamber. And what we find is that at sedentary conditions, sitting there working on a computer, I quickly go from what's an excellent indoor air quality of 500 ppm of CO2 to where I'm getting to ASHRAE ventilation threshold within a matter of minutes. I stay in there for about 40 minutes, and now I'm at extremely unhealthy conditions. One that if there's an infectious person in there, someone else is going to get sick for sure. If I have any kind of physical exertion, here where I'm just lifting a weight every 5 seconds, a 10-pound weight, 3 feet, and then putting it back on the ground, that's about 4 times the CO2 output. I need 4 times the ventilation level with that activity. We need to change ventilation level based on occupancy or activity within our homes. And then VOC output. Why is Alex, my business partner, put out more VOCs than me? I don't know, and I'm not going to take any cheap shots at why that may be true. But when you look at the list of things we're putting out, it might be kind of horrifying to you, but we're very complex chemical reactors. And there's dozens of other compounds we're putting out as well. And it turns out we're actually putting out about the same amount of VOCs as what California allows in a 2,000 square foot house as far as formaldehyde release. And if a home did have poor material selection choices and chose materials with VOCs and other significant outgassing chemicals, these would layer on top of these VOC readings to trigger fresh air ventilation in a smart ventilated home. And I'll mention, even at these levels, this is not an odor that you can describe. It's not like you walk inside and you say there's a smell. Well, what do we know about CO2 and our satisfaction or dissatisfaction with the air? We tend to survey and ask people about their dissatisfaction because that's a much clearer cut measurement than somebody who's neutral or satisfied with air quality. And we find that at today's building standards, which basically are 20 CFM or less per person, that we're going to have more than 20% dissatisfaction with the air quality in the building. And we're also going to find that sick building syndrome is quite common. And we see that carbon dioxide and dissatisfaction strongly correlate. They're strongly linked. If we go over here to about 40 cubic feet per minute, that means that we're keeping the air at about 800 parts per million. And that means we've reduced dissatisfaction a significant amount. You can see how this starts tailing off, and it's hard to make everyone satisfied, but we've significantly reduced dissatisfaction, and we've also eliminated sick building syndrome. The other thing that 40% CFM does, it improves your cognition capability, your creativity, your decision-making skills, your ability to organize information by about 10 to 12%. It has a value of about 50 cents per hour, that 10% cognition improvement. This change from 20 CFM to 40 CFM, and this is from real field data, real studies with thousands of people, something you can do real statistics on, that shows that there's a 40% reduction in sick days. We, on average, have about 2.5 sick days per person at standard ventilation. This drops about 1 sick day per person on average, with a value of about 5 cents per hour. 5 cents per hour, 50 cents per hour. Well, we'll look at the value of that in terms of what the potential energy costs would be. And I just want to say this very significant study from UC Berkeley showed that 80% of our buildings have greater than 20% dissatisfaction in air quality and comfort. This is horrendous that we allow something to be built with this level of dissatisfaction. Here's some screenshots. Big box stores surprisingly have very, very good air quality from my experience. Aircraft, maybe they're doing 20 air changes per hour, but when the volume they stick you in is quite small, that's unacceptable air quality, as shown by this reading. Hotels, they're all over the place. Your car, keep it in vent mode, not in recirculation mode. And other, it's all over the map. And again, none of these places smell. Carbon dioxide is your gateway for knowing your ventilation amount, because we saw it's associated with dissatisfaction, but also with your cognition and your sick days. At 800 parts per million under normal metabolic sedentary conditions, office work conditions, that means you're getting 40 cubic feet per minute of fresh air. At ASHRAE ventilation standards, we're somewhere in the 10 to 20 cubic feet per minute per person, with about 1,200 to 2,000 parts per million. And as we mentioned, your activity level is important. A factor of 10 between sleeping in terms of metabolic units and carbon dioxide output, and then heavy exertion. Exercise, as we saw from that chamber experiment, my CO2 output went up by a factor of 4 from my sedentary output. And that does mean you need 4 times as much ventilation. Florence Nightingale had it right when she said, if you don't move air throughout every space of every building, sickness is sure to follow. And there's no excuse for not monitoring CO2 in the air flowing through a building and in every space within the building. Today's technologies allow us to have battery-free, wireless, convenient CO2 and VOC monitoring. Wearables are coming along, and then sensors that are placed within our airstream, a VOC sensor and CO2 sensor. So we have the capability to do the smart control everywhere, in our homes, in our schools, and in our businesses and public gathering spaces. Now, here's the cost. If we did no heat recovery and it's 22 degrees outside, similar to what your January average temperature might be, this is what we have in Illinois, and I'm keeping the inside at 72 degrees, and I have a heat pump with a heating seasonal performance factor of 10. And if I have 20 CFM per person flowing into the house, and again, no heat recovery, that's a cost of about one and a quarter pennies per hour per person. I double that ventilation flow without any energy recovery. I'm talking about 2.5 cents per hour per person. A differential, again, without any energy recovery, of 1.5 cents per hour per person. That's what we're talking about. When you're not there, don't ventilate. When you're there, ventilate at this rate. It's not expensive, and I think you're worth that much. So pre-ventilation. This is a concept that we've developed. It means pre-ventilation, and it means pre-ventilation, thinking ahead to ventilate. And the reason for that is that as we have smart ventilation systems that monitor what's going on in our building, and we can talk with Alexa or conveniently collect our biometrics through a watch or other devices, as well as log the things we're doing, who we're having lunch with, and in other seamless manners, collect data that we use to benefit ourselves, that I use my data to benefit me, and your data to benefit you, and my data to benefit you. That collectively we can help ourselves understand what makes us feel good, what makes us not feel so good. There's real reasons why we get migraine headaches, bouts of depression, why we have asthma attacks, sinus attacks, and other afflictions. And we're getting to a stage where we can monitor all of the disparate reasons that go into why we feel good and why we don't. And if something is impending, that perhaps we can get smart enough to get us on another path that mitigates the next migraine or eliminates an impending bout of depression. And so we're very, very much focused on how to make us feel better and using today's technology to do that. And on our website, you can see all my data. It's been logged for years. It's live data. You can see the archive data. You can see how the controls are set for the smart ventilation system in my home. It's real and it's here today. And so to conclude, we must manage moisture. Our health depends on it. And the cost of managed moisture is not more than your health. It's much, much less. And the same for air quality. We should double today's unacceptable, inadequate ventilation standards. We need to double it for our productivity, double it for our health and well-being. Today's ventilation standards, they're wasteful. They don't get the fresh air where you're living, and they waste a lot of air that's delivered to unoccupied areas. And they tend to not recirculate. Recirculation is essential. It makes use of air delivered in unoccupied areas, and it filters the dust and the particulates building up just from your activities within the building. So thank you very much again for this opportunity to speak to you. And for any questions, please feel free to contact me at any time. Goodbye.